Hey guys, welcome, and today's lesson is going to be about osmosis. Okay, so what is osmosis then? Osmosis is the diffusion of water through a membrane. Okay, so diffusion of water through a membrane is osmosis. So what's diffusion? If you remember from previous units or previous videos, diffusion is a movement of a material or molecule from areas of high concentration to low concentration. Okay, so we need to understand that we have this cell, and in there we have a certain concentration of water. And let's say these blue molecules are water. So I'm just going to label that blue equals a water molecule. Okay, and maybe the red molecule represents something like starch. Okay. All right, well, let's see. We have to put this cell in a solution then. So let's draw in a beaker. Okay, and in this beaker, there's going to be a certain concentration of water. Okay, so basically we have, we place the cell in a beaker of water, and you can see that there are less water molecules, or not less water molecules, the water molecules are more spread out outside the cell. So if we had our water here, here, and here, and here, and here, those molecules are more spread out than what's in the cell. They're more closely packed together. So we say that the water is less concentrated outside the cell and more concentrated inside the cell. Well, what's going to happen to the overall movement of water? Well, we need to draw in a semi-permeable membrane to show that movement. Okay, so when it comes to cells, we need to talk about a couple of different types of solutions that a cell can be placed into. And I want to stress that these are the solutions that the cell is placed into. So that's where they get their name from. So what do they look like, and what are they? So the three types of solutions that a cell can be placed into are hypotonic, hypertonic, and isotonic. And we're going to look at all three. Well, in the chemistry world, you know that hypo means less, like hypothermia, but less tonic. So we have to think about tonic being the salt or the dissolved minerals in it. So, so what is that going to look like? It's going to look like it has more water concentration and less salt. So let's take a look at what that solution would look like. So we've drawn in our hypotonic solution. Remember, we're comparing the outside of the cell to the inside of the cell. So where is there the most water? Well, if you look at all those blue molecules, the blue molecules are the water. Remember, that's water. And we can say the red could be something like the salt. Okay, so if we, I didn't actually want to count these up, but you can see outside the cell is mostly water. So there's more water outside the cell. So more, let's just draw that in blue. Okay, so we have water, or higher concentration. Here, we should say water here, and less water inside the cell. So what's going to happen to the overall movement of water? As you guessed it, water is going to have more of a tendency of diffusing into the cell than diffusing out of the cell. So the cell will gain water in a hypotonic solution. So you can see that more water enters the cell than leaves the cell when the cell is placed in a hypotonic solution. So basically we'll have, we can see this water is moving in, water is moving in, water is moving in all different directions here. But water may only have limited chance to leave the cell here. So we definitely have a lot more water entering the cell than we do leaving the cell. And you can say that the cell is enlarging in its water content in a hypotonic solution. Okay, let's look at what a hypertonic solution is now. Hyper being greater amount, greater tonic. So let's take a look at this. We'll draw our cell in here. And let's say we'll try to draw in those water molecules again. And of course there's going to be some salt in there as well. Okay, but now remember, yes, there's going to be some water surrounding the cell, but a lot of that water now is replaced with salt. So remember, hypertonic, greater salt. So in this case, greater amount of salt is in the solution that the cell was placed into. So if you look now, more concentration of water in the cell than is in the solution outside the cell. And so what's going to happen is water is going to have a greater tendency to leave the cell than enter the cell. Okay, so in a hypertonic solution, remember we said the solution has a higher concentration of salt than what is in the cell. So this solution right here, we have higher amounts of salt. What happens is more water will diffuse out of the cell than will enter the cell. So we have this water leaving the cell, losing water. And maybe this one might go back in. But basically we have more water leaving the cell than entering the cell in a hypertonic solution. Finally, we have our last type of solution we can possibly have, and that's the isotonic solution. If you remember from math class, we use iso a lot, like isosceles. And what does that mean? Iso means equal. So think of the word equal when you think of isosceles or isotonic. So how would we set that solution up? Well, what we have to do is have an equal amount of salt on the inside of the cell and the outside of the cell. So they're equal concentrations. So let's draw in some salt. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So but we want to make sure it's, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9 approximately. Let's have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so we have twice as much water as we do salt. So in the cell, we should have twice as much water as we do salt. So we'll draw some salt in. So let's say we have 1, 2, 3, 4. Okay, you know what twice as much of 4 is. It's 8. 1, 2, 3, 4, 5. 7, 8. Okay, so basically what we have here is the concentrations are equal in both outside the cell and inside of the cell. As you guessed it, there should not be any overall movement of water. Yes, water will be moving both in and out of the cell. It will happen in equal amounts. So there's no gain or loss of water for the cell. Okay, so in an isotonic solution, since the concentrations of salt are equal on both the inside and outside the cell, the concentration of water does not change inside the cell. Remain the same. Okay. Okay, if you look at this diagram of this concentration gradient, you can tell that on the left, inside the cell, a greater concentration of water. So just with the random movements of these molecules going in all different directions, and that the chances or the overall chance of the water going outside the cell is greater than the other way around, the outside water going in. So overall diffusion of water will happen going from inside to outside. Now, this, you might realize, this is a hypertonic solution. This over here, hypertonic. Okay, hypertonic. Sorry, no, that's a mistake. This is hypertonic. Oops, sorry, shouldn't be right on the fly. Hypertonic. Okay. That's better. Hypertonic solution. Greater amount of salt on the outside of the cell. Water is moving from inside to the outside of the cell, or the cell is losing water, I should say. Okay, so you can see here that we have a greater amount of concentration of water outside the cell than inside the cell now. So the overall water movement or diffusion will happen in this direction here. And of course you can have water going in that direction, but overall these water molecules, more of them will pass through the membranes, or through the membrane, going towards the inside of the cell. You guessed it, this is outside the cell, this is a hypotonic solution. Less salt, greater amount of water. Okay, in this solution you can see that there's an equal amount of water on the left-hand side than it is on the right-hand side. So we would have an equal amount of chance of water going in, or outside the cell, I should say, and inside the cell. So this one might go in, this one, or that going out, that goes in. So basically we can have the overall movement of water is equal. Okay, and what do we call that type of solution? Of course, isotonic solution. Equal. Iso meaning equal. So why is osmosis considered to be passive transport? Passive meaning no energy expended. Okay, so no energy expended. How is that possible? Well, that's possible because molecules move randomly as long as they're not at absolute zero. If they're at room temperature or greater, or even lower than room temperature, those molecules will be moving, especially if they're in a liquid or a gas. So we have molecules just moving randomly around. That's all they're doing. And they just randomly either enter the cell or leave the cell. That didn't take any energy by the cell. So that's passive transport. No energy expended during diffusion or osmosis. So active transport is the opposite. Now notice we have a hypotonic solution here. More water is outside the cell than inside the cell. So water is going to have a tendency to enter that cell in more numbers. So like I said, higher numbers here than out there. So what's going to happen is that the cell is going to fill up with water. So when water does start filling up here, more water gets too concentrated, cell is going to have to expend energy to get that water to go the other direction against the concentration gradient. And since we call this energy, the energy going in here, this is ATP. It's energy currency. And you convert that to ADP. And so that takes energy to move molecules against the concentration gradient. That's what active transport is all about. Okay, well, thanks for tuning in, and hope to see you in class. Bye.